Okay, so welcome to the Arc Science seminar, and this is lecture 3 by Apoorva Khare on higher order Verma modules and positive. What is it? A positive formula? I should know it by heart by now. Yeah.
Something. Yeah, okay. We will. Yeah, I won't discuss the positive formula, but thank you again. And I promise this is my last lecture in this series. So yes, let me just quickly remind you of the modules that will be really the key players and the key object of study in today's lecture. So just to set some notation again, G is a complex Casimir algebra with the usual notation, the triangular decomposition, Weil group, Borel, Katan, and so on. I will denote the set of Lincoln diagram nodes, and for every weight lambda and H star, I define the integrability of the lambda to be precisely the directions along which I can take quotients of the Verma module by these guys, by fi power this number plus 1. So for that, this number is a non-negative integer, and that's what I call J lambda. And now to define the higher order Verma module, as we call it. So this is going to be given by, first of all, the data is lambda and H. And script H is a collection of holes, meaning sets of independent subsets of this J lambda. So Lincoln diagram simple nodes, simple Lincoln diagram roots, which are pairwise orthogonal. Okay. And so H is given a collection of such holes. We define M lambda H to be M lambda quotiented by exactly all of these things, right? So for every hole, you define that specific lowering operator product, apply to the highest weight vector of M lambda, and take the submodule it generates. Notice that each of these guys is indeed a maximal vector, and therefore the submodule it generates is a Verma module. Okay, so each of these guys is a Verma. So M of, let's see, product H in H. SH dot action. So this is the Verma submodule. Sitting inside this Verma module, you take the sum of all these guys as they embed in here, and then that is big submodule, quotient it out. That is the module M lambda H. Okay, and these are the modules we will study in this last talk. So for example, if I quotient by nothing, if there is no denominator, meaning 0, then I get the usual Verma module. If I quotient by, with the H consists of singletons. If I basically quotient by F1 power lambda of H1 plus 1 and F2 power lambda of H2 plus 1 applied to M lambda, then I would get a parabolic module or generalized module as introduced by Lepau's. And so each of these guys has some universal properties, and that's what I will count in general. So if any G module V has a maximal vector, maximal means it's killed by n plus the raising operators, and it is it's a non-zero vector with it's a weight vector in V, meaning H acts by lambda H. And as well, I have FH. The FH means, actually I should have written it out, but FH just means the product of the FH. Product H and H. Acting nilpotently for all holes in the set script H. Then there exists a non-zero module map phi from M lambda to V. That happens even without this nilpotent part, which sends the generator M lambda, the cyclic generator, to that lambda. But now, because of this extra nilpotency part, this map factors through the map from that module M lambda H to V. Okay. And then so this nilpotent part here is what we then abstracted into something called the the higher order category O. And so let me erase this and just quickly write down the higher order category here. So M lambda H belongs to category OH. This was defined. I won't define the category O because that we said last time, but that was a nice abelian finite length subcategory of G modules. So OH consists of all objects in O. It's a full subcategory. The morphisms between objects.
No. Last time, Apoorva,
yeah,
you did only for G semi-simple. This so it's.
Oh, sorry. Yes. Here I need to define this semi-simple. Thank you. That's right. Such that this condition happens. FH acts nilpotently on M for all M. On every vector, each of these acts nilpotently and for all these. Okay, that was category O, and then we wrote down this theorem. Write that down. So first of all, OH is an abelian finite length subcategory of O with enough projectives and enough injectives. So every module is a portion of projective and a submodule of an injective. Second, now this was the part about the BGT reciprocity. Just remind you again. So the point was in the usual category O, every object, every projective in the usual category O, or also in the first order category, parabolic category O, as a filtration, as a finite filtration by standard objects, by objects some points. Let's call this Pi. That was my notation last time. By some objects Mk, and then each Mk, of course, is being finite length. Each Mk has a finite Jordan-Rotor series in terms of the Lj's. So the L lambdas are like the L's, these are the simple objects. The M's are the Verma modules or the parabolic Verma modules, and the P's are the projective covers. And then we sort of said that the point is how do you determine this Caldera matrix? We have Pi is to Lj. Well, the point is each Pi consists, you can, in the Grothendieck group of category O, you can write down the class of Pi as a sum of the classes of the MKs that occur in that finite filtration. And so the number of times Lj occurs in Pi or in the class of Pi is the summation over how many times Lj occurs in each Mk. This should be something like this, sum over all K, Pi, how many copies of Pi, how many copies of Mk lie in Pi, times how many copies of Lj lie in Mk. That's what I said last time. So if this matrix we call as C, and this matrix we call as D, then the point is, first of all, we have this nice phenomenon called BGT reciprocity, which says that Pi is to Mk is exactly Mk is to Li. And then this is again Mk is to Lj. But then if you look at the ijth entry of D transpose D, so this is Cij, which is Pi is to Lj. This is Bij, Dkj, yes. And then if you look at the ijth entry of D transpose D, that is exactly this sum, because this is how we multiply two matrices, or one matrix times its transpose. Right? That's why when I said last time that C equals D transpose D, that's exactly what we have meant. And so that's why C is symmetric, because this matrix is symmetric. Okay, so this was the BGT reciprocity. So it has two parts. First of all, every projective yes, now let me see. How did I write this in what notation? Sorry, where is the here? Category O. Every projective, and I think here I do give the fact that for G equals SL2, only for copies of SL2 is what we prove is every projective in category OH has a standard filtration. And when I say standard filtration, I mean the subquotients are the subquotients are exactly these modules m lambda comma h prime. Okay, and so the point is it's a projective of so every projective is a direct sum of indecomposable projectives. Everything is finite length, so there are finitely many. Each individual indecomposable projective is the projective cover of some simple module in that category H. Right? So it is some like it's pH of mu. Right? So now that means I'm saying something like pH of mu, where L mu belongs to OH, has a finite filtration in terms of such modules. And so which H prime occur depends on mu and lambda and H. Yes, that's how it depends. And so the point is the same lambda and different H primes may occur for different mu's in the same block of category. And then the third part of the BDG reciprocity doesn't quite hold, but it does sort of. So what do I mean? So before I tell you the third part, then let me again remind you of the example from last time. SL2 plus SL2.
So when you say standard filtration via m lambda h prime, you mean the quotients, the subquotients are m lambda h prime. That's what you mean? Okay.
That's so it is not too far from the original picture, but there are subtleties. Right. So let's see. So first of all, let's do an example of what can go wrong. I said this last time, so quickly let's do this. And as I said last time, we will restrict to the block of lambda equals 0. So we'll work with and the H set is the single set. All the other possible H sets give you either the usual category O or the parabolic category O. So that's already known. And then BGG reciprocity holds as usual. So here we work in the category OH, intercept, intercept O, W dot lambda. Okay, and so then there are three simple objects, as we said last time. So first of all, this means that F1 times F2 acts locally nilpotent on every object. Now, in particular, if you look at L0, 0, 0, yes. So L, this is lambda. So L0, 0 is just one dimensional. So on that, of course, this kills it, the highest grade vector. But if you look at, and it does the same for this module, this simple module, and this simple module. 0, minus 2 and minus 2, 0. But for minus 2, minus 2, which is S1, S2, dot actual lambda, the simple module here, in fact, the Verma module here, is in fact simple. And the Verma module is never, this does not act nilpotently. In fact, it acts freely on the Verma module. So this object is not in the category OH, the other three are. And then so we have three simple objects, L lambda is 0, said. L of S1 dot lambda, L of S2. These are the three objects that belong to this category. And then as we said, there was this Cartan matrix for these guys. The Cartan matrix. So okay, this category has enough projectives, enough injectives. So you can talk about the projective cover of this object in this category and of each of these. And then the Cartan matrix was recomputed last time, or as I told you last time, and I will actually work it out today. Was this. And this is never equal on the nose to D transpose D for any D in with non-negative integers. n cross 3. And because this can never equal such a matrix, therefore BGG reciprocity cannot hold on to those, because no class of intermediate objects can exist. Otherwise, you would have such a decomposition matrix, where this was the matrix of Jordan-Holder multiplicities of simples in the standards. But the fact that such a matrix doesn't exist means such a class doesn't exist. Nevertheless, some form of BGG reciprocity holds, and that is what I will tell you here. And so for that, let us understand, let me tell you what the how the projective covers look like and what are their Jordan-Holder schemes. So first of all, there is the projective cover of lambda, and then the projective cover. So 1 dot lambda, and so what I want to tell you now is literally just the structure of these. What are the standard filtrations for these three objects? That's all I want to tell you. And then that way we will see what kind of reciprocity holds. And it holds not just over SL2 plus SL2, lambda equals 0, but SL2 power n and every lambda and every h as well. So in G equals SL2 power n for all lambda in H star, for all, of course, for all n, everything equals 1 for all lambda in H star and for all whole sets in indefinite. So that's BGG reciprocity. Some version does hold. In complete generality over SL2 power n. Okay. So for that, as I said, let me just show you the structure of these projectives here. The first one here, this projective, this actually is, so PH of 0, 0, if you will. This is actually the standard, the second order Verma model. Sorry, oops. M of 0 power h. What is this? This is literally M of 0, quotiented out by F1, F2, and 0. UG. I read the full line. So this is the subject, the second order of the model. This actually is the projective, and that is exactly, so there is this heuristic, if you will, that in a block of category O, in the block of category O, for the highest weight in that block, in this partial ordering, the Verma is projective, and that is exactly pretty much the same thing. This is the Verma in that block, in that higher order category, and this is projective. And similarly, in the highest, in that block, for the lowest weight, the Verma is simple. Well, okay, we don't have the lowest object here because that doesn't belong to the category O. But indeed, of course, L minus 2 was Verma itself. Okay, now let me tell you the other two standard filtrations. So here we go. The projective covers are, so the pH of S1 dot lambda. So every time, so remember, this is this thing I mentioned last time. Right? If you have a projective module, so if you have a simple module and you have a projective module, so of course it subjects onto it, but the Verma module of the standard object in that category also subjects onto it. So you actually get, and you get a generator mapping to the generator mapping. So that's what happens in the usual category, and it also happens here. So of course, these three objects are in category OH, but now what I will say is, first of all, this is M SI dot lambda. So I need space to write this. Where do I write this? So we have pH. This is projective in that block. SI dot lambda. This subjects on the parabolic Verma module. M same highest weight, of course, but the integrability is in the other direction. And then here you get, okay, and then again in keeping with heuristics in category O, or general principles, the first term, the radical basically, the top term, but the quotient is not simple. The top term in the Verma flag, in the standard filtration, is with the same highest rate, and all bottom terms, all terms below in the kernel of this have strictly higher rate. So when if you have SI dot lambda here, and the J basically the I and the J are just either I is 1, then J is 2, I is 2, then J is 1. Okay. So this is the Verma module with this Verma module, but then you quotient out by the other integral. So then that is how, if it is this Verma module, then we are saying that sort of we don't want, because you took SI dot lambda, you took S1 dot lambda. F1 cannot act nilpotently on the lower vector, a vector of the lower weight in the dot of, right? So because F1 times F2 has to act nilpotently, we better have F2 act nilpotently. That means we must quotient by this part so that we get this parabolic curve. Otherwise, this condition will not be satisfied and this object will not be in the category. So if you take highest weight to be SI dot lambda, then Fi cannot act nilpotently. Therefore, Fj had better act nilpotently, so you should quotient out by the Fj. So that's the kernel, and over here, the only strictly higher weight is lambda. This is m lambda, and then but the Verma module again doesn't remember. This is the Abelian category. This is the object in the category. This is the sub object in the category. F1, F2 has also to act nilpotently. And so, what should this one be? Well, this one is going to, I think, still be just J. Yeah. So one can verify that this is the standard filtration for the projective of this of either of these two projectives. But you see here the point was the whole was 1, 2. So this is M0 quotient by F1, F2. This is M0, lambda equals 0. Or M0, 0. Quotiented just by Fj. Ug times Fj. So this is a different, you are quotienting by a different thing that you are quotienting here. That's why different Vermas with the same height, different whatever, standard objects with the same highest weight and 0, 0 occur in the filtrations, the standard filtrations for different highest weights. This one has this standard object with highest weight 0 occurring, and this one has the So that's why BGG reciprocity. So now what does the BGG reciprocity theorem say here? And what it says here is the following. Let's see, something like the following. Take the projective of a mu, right? Okay, and then I want to write down something like this. I want to write down the m lambda, I guess. Should I say lambda? No, I want to say mu prime, just for fun. I don't want to confuse lambda as just the highest object. And h prime, I want to look at this multiplicity. And I want to say this is equal to m, I guess this should be mu prime comma h. So somehow these are smaller h's, these are smaller holes than the hole that we are working over. So we take the biggest object like this and look at L of mu. So this multiplicity should equal this for what mu prime? Sorry, for what mu prime is fine. Mu and mu prime are fixed. So I want to say something like this happens. It doesn't happen on the nose because well, you can check from here. But, or you can check from this matrix, not weakly transversely. It does happen when I sum over all. So fix my mu for all mu and mu. Fix these two objects. But the moment you fix these two weights, then the right hand side is still the multiplicity of some simple object in the standard Verma, in the standard module in that category. M mu prime h. H is the same as the OH. On the right hand side, on the left hand side, however, I should take that same the projective cover in that category of L mu. But then here my mu prime is still fixed, but the h is allowed to change. And if I sum up over all of them, then I get the. So that is one thing. And but anyway, so it's a VGG type reciprocity, but not on the nose. And the fact that it's not on the nose is already good. And statement number 4, which I didn't, which I of course mentioned last time, but did not write it, is C is not equal to D transpose B, but C does equal C transpose. Again, all of these things are over simple problems. So part 2, 3, and 4 are over a simple power. This is just the Tata matrix of Pi, P of Ph of lambda is to L of mu. This matrix is symmetric. Again over a simple power. But again for all lambda and for all H and for mu. Okay, so that is the reciprocity, and so maybe we should. I think that was everything I had to say about this.
No. I have questions.
Yes.
So this H primes are less than H, or what is the idea? H prime is contained. What is the relation between H prime and what is the sum over left hand side in your theorem?
Right. The rough idea is you basically for every mu, so you are given an H. Okay. For every mu, such that L of mu first of all has to belong to the H. So you only care about those modules sitting inside the category. Only they are the only ones who can occur as Jordan-Goldman factors of these guys or these guys. So the first claim is if this object occurs in the category OH, then L mu prime must occur in OH as well, because L mu prime is a quotient also. This is the highest rate module, and this is the abelian category. So if this occurs in OH, then L mu prime occurs in OH. So first of all, there is a constraint on which mu primes occur in any filtration. Because, for example, this only has 3, not all the 4 objects in the usual block of category. So that is the first point. So first of all, consider a mu such that L of mu occurs in. Sorry. So, and then for this mu, what I think, as far as I remember, what you have to do is the H primes that occur. You look at the following. You look at J mu is the integrability of mu. That can reduce. You see here, the integrability of mu was 2, but here the integrability of mu was only J. Sorry, the integrability of lambda here is 1 comma 2, because lambda is 0. So 0 of alpha HF is always positive. But the moment you do this, you get a -2 in one of the coordinates. And so the integrable directions are less. The I is no longer integrable, so it's only J. And then your quotient will be that. So here, as far as I remember, and this is where I thank Teja for being in the audience, I look at these things. That's my strength. Strictly, I should say a little more technically, like extra, I mean, the other one, the minimal goals, but is that correct, Teja? I don't know.
Yes, sir. Yes, sir.
So this is these objects are standard objects in your category.
These objects are
standard in your category.
Yeah, they are. Actually, or in fact, is H prime equal to that, or can H prime just contain?
Containment is enough, sir, and we want each of them to be non-empty. Otherwise,
H prime is contained in this. This is H prime mu as we call it. Right?
Yes, sir. And each of them should be non-empty. Then only L mu belongs to that.
Each of them should be such that L mu belongs to you.
They should be non-empty. We should say that they should be non-empty. Every hole should intersect J. That is one important.
Sorry, and what should I say here? Okay. And L mu belongs to OH means these are non-empty, but H prime is contained in that is such that.
We are summing over all H primes containing these holes, sir. These refined holes.
Yeah. That's what we sum. And so, of course, a bunch of times this multiplicity will be 0. Many times this multiplicity will be 0. In fact, here you see that lambda, m lambda comma h occurs in some projective filtration. M lambda comma j occurs in some other projective filtration. So if I sum up over the m lambda comma j's that occur, m lambda comma h's that occur, the multiplicity of this guy will be 0, but the multiplicity of this guy will be 1 in this filtration. So a bunch of the terms here will be 0, which is fine. But in fact, I think in our case, we probably have only exactly one non-zero term in this study. So it's not even, I'm not even sort of clear on how this generalizes to other semi-simple G. If something like this holds, then does one take the summation over all of them? Does one just take exactly one term that gives you the equal multiplicity? I don't know.
No. Still, this H prime is not clear. So what is the statement? What can H? So H prime could be empty.
Yes, H prime, for example, I think could be empty, but then this model, the Verma model, would not occur in the category. So this would be OH. So it would not occur in the filtration of this. That's why a bunch of terms can be 0.
Because we want FH to act nilpotently on them. FH for H belonging to script H, we want them to.
H prime is empty, that this module won't be in the category OH. Verma module is not in the category OH because F1, F2 does not act nilpotently on any Verma.
No, so what? So sorry, I am confused. So what is that H? What is the summation over? What is H prime?
So
what is the summation over? Okay.
H prime mu to be the set of all J mu intersect H, H in H mu. This is a very precise, unambiguous definition. I have mu, therefore I have an integrability of mu. I'm assuming, of course, that L mu is in this category.
H in H min, what did you write there?
H in H min, exactly.
Okay.
The moment I have that L mu belongs to this category, one can show that this set is always non-empty for every min or other. So the empty set does not occur in this collection because L mu is in this. The moment the empty set, see, the problem is if the empty set occurred in the collection and you quotient it out like this, you would get a 0 module. That doesn't happen. So first of all, that is the first step. The empty set never occurs in this collection. Okay. Now, secondly, now here I can just go back. Sorry, am I saying mu or mu prime here? Just forget that. Must be mu prime.
Right, H prime, mu prime makes sense.
Because I care about these guys, not about. Oh, it's not even a, it's not a code, it's a contains that. It's immediate. Yeah. But the notation in our paper is slightly different, but yeah, that's exactly what it is. It contains these guys and it is uppermost. So look at, so what I'm doing here is the following, right? Don't just look at J, look at the upper closure of J in the set of independent subsets of 1. If it is J, then the upper closure of J is the collection J. Basically, Fj kills some highest vector. What are all the other things that kill the highest vector? Fj and F1, F2. Fj is either F1 or F2. So if F1 kills the vector, then F1 times F2 also kills it. So the upper closure is I comma F1. And this set clearly contains the set which I started with. Okay, so this set is contained in this set, even though I started with a smaller set. Because I look at the upper closure. So if you sum up over all the H primes, if you sum up all the H primes containing this definition, H prime mu prime, which are upper closed themselves, then they will look like this. This stands for to quotient the Verma module by just Fj power lambda of Hj plus 1. is the same as quotient taken by that vector and by F1, F2. So in particular, it also quotients by F1. And so if nothing else, you can say this is some technical thing you sum over. But yeah, sum over everything, that all the holes here such that they lie in the category OH. Basically, this condition is to ensure that the holes lie in category. The moment you have an upper closed set containing these guys, containing any H, then the relations in H are satisfied here. So therefore, it's a further quotient, it's an extra quotient of mu prime comma H. And mu prime comma H lies in the parabolic, sorry, this higher order category OH. Therefore, its quotient, which is these guys, whenever H prime is bigger, so you quotient by more things, also lies in this. And now run over all the possible such iterations. At least one of them is non-zero. And so far in what we encountered, exactly one of them was non-zero in such a iteration. And then that the sum of those non-zero multiplicities, in this case, exactly that specific non-zero multiplicity, only one of them was non-zero, but whatever, the sum of all of them is equal. As I said, I don't know what happens for others. Starting even from part 2. Does part 2 hold? Does part 3 hold? And in particular, does part 4. So SL3 again is fine because rank 2, there are no actual higher order holes except in SL2 plus SL3. So SL3 is fine. G2, B2, they are fine. SL4, I don't know. So we don't know what happens in SL4. But at least this is a start. And we do know that some kind of reciprocity does hold, even if it doesn't do it. Okay, so maybe that was everything I had to say for the
Apoorva, for clarity, so can you say that for other, I mean SL4 or higher, something definitely does not hold? Is there some caveat, or is
yes,
it?
yes, I forgot to mention that. I said it last time. So in any D algebra of rank 3 or 4, there is at least one H for which reciprocity is not chronology, and it's not even something non-trivial if G semi-simple of rank bigger equals 3.
Sir, you also wanted to say that it's not highest weight category.
In particular, it's not highest. So, exactly. And the reason why this is true is because you can basically do the following. Right? So suppose G is not semi-simple. G is semi-simple, but not of rank 2 or 1. Then the diagram, the linking diagram of G is not complete. So you can, in particular, there are two nodes which are not connected by H. Let alpha I and alpha J. Then alpha I be orthogonal to alpha. I can decide. Right? I can do this. I can pick some two nodes which are orthogonal. And now what I do is choose lambda to be generic with respect to the remaining guys. Lambda generic with respect to I minus I comma j, and such that lambda of alpha I check equals lambda of alpha j check equals 0. I'm really grinding backwards. My apologies. then we literally get reduced because lambda is generic with the other guys. If you look at the dot orbit of lambda, those are the only possible, the simple modules with highest weight exactly in the dot orbit are the only possible Jordan-Holder factors of Verma modules of M lambda. But there's a further restriction, right? When can M lambda contain L mu? First of all, lambda and mu must differ by some integer multiples of, must belong to the integer root lambdas. If lambda is generic with respect to all the other simple groups, then this will never happen. The only time it will happen is exactly when you have SI lambda and SJ lambda and SI SJ lambda. So the block of lambda, linkage class of block, in so first of all, the block itself consists only of four highest weights: lambda, SI dot lambda, SJ dot lambda, and SI SJ. And now you do exactly the constructions that I erased from this code. My apologies. Right? So if I comma j, that's the short exact sequences that I drew for the projectives and so on. That's why I wrote I comma j, not 1 comma 2. All this because now here I comma j means exactly that. So the moment you have this thing and you let h be let's see, h to be, these are two orthogonal groups. Okay, I take my h to be 1 comma I comma j. Just one second order. Then this situation is exactly the situation in SL2 plus SL2. There is no difference. And therefore the Cartan matrix for that is again 1, 1, 1, 1, 2, 0, 1, 0. So that is never equal to D transpose. Therefore, VG reciprocity cannot hold on to those because there is no intermediate class of objects. And because there is no intermediate class of objects, this reciprocity doesn't hold. Therefore, highest weight category also fails. Right? If it's a highest weight category, then there's a VG reciprocity. So that also fails. All of these things fail because you can just do some generic lambda. And now for that H and that block of lambda, this is the, there exists H and that's my H. And the block of lambda is just exactly the previous time. There are 3 simple objects, not 4, because Fi Fj does not act independently on this, which is a simple module and a Verma module. The same thing. So already at least for rank 3 and above, even for SL2 plus SL2, the moment higher order holes can occur, VG reciprocity fails. However, projectives and injectives do exist, and maybe standard filtrations might occur as well. We don't know. And the Cartan matrix was symmetric, so even that might happen. But again, we don't know. It's a question. Okay, so now any further questions before we finally move on to the resolutions? Okay, so the final part then talks about characters and resolutions. Okay, so let's remember the wildcard. Let's before the wildcard formula, before characters of simple modules, there are characters of Verma modules. It always starts with Verma. So let us remember the character of the Verma module. Okay, so this is what it is. E raised to lambda divided by the quotient of 1 minus e raised to minus alpha. This is the standard thing in semi-simple algebras. I'm going to say more. What the cat's movie thing. So, sorry. And if I want to do this, is basically the constant partition. And if I'm working over cat's movie, then I should write down the result. So this is the character of the Verma. And once you have the character of the Verma module, then one has the value character formula for the character of the simple element. If G is a finite type or G is symmetrizable then of the simple quotient, but otherwise, so for example, let me write down this one here. The maximal integral quotient, this is equal to L lambda if G is symmetrizable. The character of this guy, this is just the alternating sum W in W of e raised to lambda. Okay, oops, sorry, this is wrong. Should not be j lambda. Right, the point is lambda is an arbitrary rate of x star. It need not be dominant or integer. So you only take the maximal integral quotient. Okay. This is all about lambda in P plus. So let me even move all these things.
Otherwise, you have to use notation m lambda comma j lambda for general parabolic Verma.
The point is, this is exactly the parabolic Verma. That was my next statement. So, yeah, exactly. The point is, this is literally exactly this parabolic Verma. And then all you do is you take the same exact thing, except now you put a W here. And then you put a minus 1 to the minus 1 to the length of the. And so the reason why the Y character formula works is because this works actually for this parabolic Verma module. But the point is, in fact, you don't even need to take j lambda. This is true for every j in j lambda. Corollary, lambda belongs to P plus dominant integral, j equals j lambda, which is I. This is the special case which is called the line character, or the line cat's character. You're infinite, right? But the point is, it is true far more generally. It is true for all parabolic modules. All you do is you write down this thing. And now, for instance, if you know, so if lambda is dominant integral, if you're summing over the entire value, then that's the value character formula. If lambda was just in, if you take any Verma module and you don't sum over anything, then that's the trivial subgroup, which is W equals 1. So minus 1 raised to 0, e raised to lambda, that is the constant. So this formula interpolates between the constant and the Y character formulas and works for all parabolic formulas. So particularly 0 order ones, first order ones. And so it is very natural to expect that you should have something which works for higher order modules as well. So the final results that I will tell you are to indeed tell you that such a formula is actually true. These modules are indeed that natural and that fundamental, but this formula works for them in certain cases. Just like for Sn to power n, we know the answers. This formula we can prove in certain cases, and of course, it may be true in more generality, and that would be great if you know. Please feel free to work on it as well. Okay, but so far it is known over in two different settings, as I will tell you. But the point is, it is exactly the same formula. That is why these modules are natural in yet another, which also makes it rather surprising that they weren't studied until now. So let us start there with okay. Let's two settings. So let's just now how do we prove this formula? Well, there are probably different ways, but one way to prove such a formula is to produce an actual resolution of this object using Verma modules of various different height strings. And then when you take the Euler characteristic of the resolution, you get exactly this. As you see, each of these guys is a Verma module character, so you're taking some kind of a Euler characteristic of a resolution. And that is exactly what happens again in more generality. So further making them get more natural, we have a VGG resolution for higher order modules. So hence the second one. So let us start with the resolutions. In fact, I will tell you let me start by telling you the resolution. Right? So I'll tell you two. So okay, let's talk about the easiest resolution. So let's say I have M. So resolutions. The first is an obvious one, of course. If the whole set is empty, then we just get the usual Verma. That's fine. If the whole set is generated by singletons, then you get the parabolic Verma. That's also known. That's just sanity check. But that's just the known cases. Let me call it 0. Let's do 1, where there is exactly one hole. Like the case that I told you, BGG reciprocity fails. Let's just say there's just one edge. Or if you want to consider the minimal holes, there's only one minimal hole, and so H is really if you quotient by some FH product, then you can quotient by all larger strings of independent sets. So in this case, what is M lambda H? Let's write this definition down. It is M lambda quotiented by one submodule. Right? There is no summation because there is only one minimal hole. So instead of summing over all the holes, you can just sum over the minimal holes because that's the same submodule. And this module is what is UG times product H in H. Next slide. And as we said, this was exactly M of product simple reflections dot action lambda. And therefore, once you have this, okay, this is what I'm going to start calling SH. Okay. So instead of writing down product SH, H in H, I'll just say S capital H. These are orthogonal groups. Therefore, these simple reflections pairwise commute. And so it doesn't matter in what order I list the roots, the simple reflections all come. So this is well defined, regardless of the enumeration of capital H. And so this is what I call it. And so therefore, this M lambda is just a quotient of 2 Vermas. And so of course you have a BGC resolution using purely Vermas. Oops, I don't have space to do this here. MSH dot lambda M this module to 0. That's a BGC resolution because this is the object. These are the Verma modules resolved in it, the usual Vermas. And so the character, I mean, this is again obvious. This is a short exact sequence, but it's a resolution. This is equal to M lambda, or this thing is E raised to lambda minus E raised to SH dot lambda. So you see, this very much looks like this character formula. Now I'm summing up though. What am I summing up? That is the key. This is, you can say, it's the sum over W in the surprise, I will call it WH in the script H, but higher order parabolic line setting subgroup. So far subgroup. And what is the subgroup? It is just the 2 element set per subgroup, 1 or E and SH. It's basically just like SL2. There is the while loop at size 2. Except the while loop is not made of simple reflections, it is made of some weird words. But it's a product of simple reflections which are all pairwise commuting. So that part stays the same. Right? Just like the idea of poles being product of commuting lower operators, this is product of commuting simple reflections. Okay, great. And then you write down the same thing. So it is E raised to W dot lambda, W dot lambda here, divided by the denominator. And then you have to write down the minus 1 raised to LH of that. Right? Regardless of, even if there are 2 reflections here, or there are 4 reflections, or there are 5 reflections, regardless of the parity of H, I have to put a minus sign here. So I have to put a minus 1 raised to the length in this group. So think of this as a Coxeter generator, and the length with respect to this is 1, regardless of the usual Coxeter length of this, which is the number of simple reflections, which is the size of H. I don't put the size of H here, I put this. And so that's what I'm saying here. So the character M lambda comma. So that here. So in this case, the character So that is one. The claim is this happens in complete generality of some kind. What is that generality of some kind? The generality is if I look at H min, and I'll show you here. Let's say there are H1 and H2. There are two holes now. Rather than one smallest hole, there are two. And I further assume that these holes are orthogonal. Independent H1, but H1 union H2 is also in. They are disjoint, of course. Okay, I assume they are disjoint, and I assume they are independent. So every hole in H1, every simple node in H1 is not, or no simple node here and here together. None of them are connected. In that case, then you write down here is the resolution. So now what am I saying? Now my resolution looks like now I have a what? So m lambda h. Again, you can just quotient by a sum of two things because you can sum over the minimum things. Is n lambda quotiented by ug. Okay, let me give this a name. I'm sick of doing this. Let's call this f h lambda. Because the lambda part means that I raise each component to the correct power, not all of them together. F, the h part is how the h part tells me which powers I raise the individual. So f h1 of lambda bracket m plus and now because I know that these are independent, therefore these lowering operators also commute and they have nothing in common because they are disjoint. They have nothing in common and they commute. Okay. And then now I have again a resolution. So let's write this down. So 0 goes to this n lambda h. The first obvious object is that the Verma module was subject to it. Now, what is the kernel? Well, this module is isomorphic to SH1, S capital H1, the product of the simple guys, dot lambda. Direct sum MSH2 dot. Okay. And then what happens in between? Then the kernel of that is going to be MSH1, SH2. Because all of these are disjoint and so on, these two also commute. Everything commutes. Should I use weird snaky business? Okay. Sorry. So yeah, so this is the natural surjection. This is just a quotient of the lambda. So that is the surjection. Okay. This one here is the following. How does this embed? Well, we know exactly how it embeds. So let me call this phi. This is D0, the differential. This is D1. This is D2. Let me tell you what is D1. D1 of, remember these are Verma modules, right? So, sorry, what is going on? Should just make this, don't disturb. Okay. So, so these are Verma modules. So let's call this lambda 1 and lambda 2. So D1 of, let's see, x1 m lambda 1 and x2 m lambda 2. And so x1 and x2 are in UG, UN minus. Every Verma module is freely isomorphic to UN minus. So x1, x2 in UN minus. Right? So this is equal to, well, how does this module embed inside this module? It embeds exactly via this. So it is x1 f h1 of lambda plus x2 f h2 of lambda. That whole thing acting on m lambda. So that is how we get from this module to this module. There's a name for that. It's written down in standard notation as FH1 lambda FH2. Meaning you take this row vector and dot product with the column vector. And this name, this kind of notation wasn't made up by me. It is exactly what you use in the Kosovo resolution. Because you use it because this is the Kosovo resolution. I don't want to. This is not some big surprise. Okay. And then similarly, I'll just write down the D2. And I will most likely get some sign wrong, so that will correct me. If you have D2 applied to any vector, now how does this vector embed inside? How does this Verma module sit inside these Verma modules? Well, it sits inside this by multiplying by FH2. And it sits inside this by multiplying by FH1. So D2 of, let's say, X times M, I'll call it lambda 1, 2, just for fun. So lambda 1, 2 is SH1, SH2 dot lambda. Okay, and then this is, and now I need two coordinates. And the first one is going to be minus FH. I want to put it as minus FH2 times, sorry, minus X times this, I suspect, times M lambda 1, and then plus X times FH1 lambda M lambda 2. And so again, you write this down in here in the usual way. This is what you write down as minus FH2 lambda and plus FH1 lambda. And now we see that the dot product between this and this is 0. That tells you that the differential square to 0. The other two differentials clearly, the other differentials clearly square to 0, but this is the only contrary to that, but the dot product is 0, so you're done. Right? But then you need to verify that this is complex. So this is indeed a complex, you need to verify that this is exact, hence gives you a resolution. And that is basically because, so this is complex. And it's exact because it's a Kosovo relation. So really what you're doing is the following. You're really working over not the full U of n minus. So this is over some Kac-Moody algebra and the holes are orthogonal. But really what you are working over is the polynomial algebra in these two variables. So we are working really over, let's say, the commutative ring. In these two variables. Over that, you write down this, you build this entire complex, make it work because the differentials only involve elements from this thing. And then you say, eventually you say, I'm going to tensor the whole complex over this complex over R over with UN minus, which is a free R module. And then because it's a free R module, then from life stays good. Life stays exact. So step 1, work over this module, where this is precisely the Kosovo resolution. The Kosovo resolution of what? I'll say that in a second. Tensor over this thing. It's free by if you want the PBW theorem or something like that. So Kosovo resolution of R mod R y1 plus R y2. Y1 equals this guy, y2 equals this guy. So this is exactly the Kosovo resolution. I'm not even taking the polynomial algebra in the individual lowering operators. I'm taking all of them together as y1 and all of these together as y2 and only looking at that. And because of the PBW theorem and so on, everything is life stays. Okay, so if the point is in general, therefore, let me just, I'm not going to obviously write down the general picture. I will share my screen. Okay, here we go. Okay, so pairwise of BGC resolution. So So the higher order Verma modules are crucial in understanding the weights of V. We understand their weights, and do we now understand their characters? So first of all, for the usual Verma, we had the constant function. For the parabolic Vermas, we had the Wildcat's formula, and what happens in higher order. Right? So the first thing that I said, first you can, for example, look at this module. You have two different holes over SLN, and the holes are orthogonal. F1, F3, so 1, 3, and 5. And together, all of these are also orthogonal. So then you write down this exact thing that I wrote down in the board. D0 is the natural projection. So D0 is the surjection, the usual one. D1 is the embedding, which is using these differentials, how they embed, how these Verma modules embed inside here, and then how this Verma module embeds inside each of these. These are very sort of easy embeddings, so it was easy to write down the differentials. Okay, this is what you can explicitly verify this by hand, but rather you should remember that this comes from the Koszul resolution, and then you tensor this. And in this case, by the way, it is also the BGG resolution over this, over the group Z2 cross Z2. But with what are the generators? The Coxeter type generators are a length 2 word and a length 1 word, meaning a simple reflection and a non-simple reflection, and not a simple reflection. Nevertheless, the group is, because these commute, the group is still Z mod 2 Z square. And so that's what it is. But the new length function takes this 2 element set, 2 element word, to have length 1. It's different length than the Coxeter for obvious reasons. It is how these occur in the Koszul resolution. And then here is the general statement. Fix any Kac-Moody algebra and any weight. Sorry. And then take a collection of holes whose minimal holes are pairwise orthogonal in J lambda. Define, as I said, SH to be this thing. Then M lambda comma H has a BGG resolution. And at each stage, you sum up over the Verma modules where there are only P many of these individual atoms, or whatever you call them, constituents. Dot action lambda. And the differential can be written down explicitly because for the Koszul resolution, it has been written down explicitly. In particular, with the while, whatever, this weird while group to be, subgroup to be Z mod 2 Z power K, generated by the SHIs, you get exactly this character form. Again, so it's exactly the same thing because it just takes the Euler characteristic of the resolution. Okay, let me tell you the maybe an open question in this. What is the simplest case when you have when this doesn't go through? So I want to take disjoint holes still. The overlapping holes are the next part. The disjoint holes and but no longer independent. So they might have they might not be orthogonal. Okay, so remember that the Verma module was this M lambda H was defined this way, right? How to resolve this if H min has disjoint but not orthogonal holes? So the simplest case again, let me remind you of all the higher order. I wrote this down for some time, but when lambda is 0 and G is SL4, then there are lots of higher order Verma modules. The extremal ones are M0 itself and 0. When you don't quotient by anything, or when you quotient by the empty whole, which means you quotient by the empty product times M lambda, which means 1 times M lambda. If you quotient by 1, you get 0. Okay, then there are the remaining 7 other first order parabolic Verma modules, which we wrote down. There are 2 second orders. So this is the one that we resolved because there's only one hole. One hole is of course pairwise disjoint, pairwise orthogonal. So that got resolved very trivially on the board. Now there are 2 holes, but the point is here these 2 holes are not disjoint. How do you resolve this? Okay, so let me write down something in general. So the way we wrote it down on the board, suppose H bin consists of 2 holes which are disjoint, but they don't need to be orthogonal. The first thing is I want to understand, you want to resolve these things. You want to resolve the resolution should be indexed by certain elements of the while group, because after all, those are the Verma modules that occur. What are these elements of the while group? So naively, if you go by what we did here, we took those SH1 and SH2 and we looked at the subgroup they generated inside the while group. So what is the subgroup that these 2 elements, which no longer commute because they are no longer orthogonal, what is the subgroup that these 2 elements generate inside? Well, any 2 elements of a group generated dihedral, any 2 elements of order 2, these 2 elements of order 2, generated dihedral subgroup. What is the order of that dihedral subgroup? Well, in this case, you know what it is. So if you look at S1, S3 times S2, and that is the that is the product SH1 times SH2. Sorry. What is the order of S1, S3, S2? Well, S1, S3, S2 in SL4 is a coxeter element, right, in the coxeter group, because you multiply all the simple reflections in some order. It is known that all of these guys are conjugate and have the same order. And the order is exactly the order of S1, S2, S3, which is a 4 cycle. So the order is 4. Sorry, I don't know. So going back to that example, consider G equals SL4, lambda equals 0, and the module that we studied above. So in this case, the dihedral subgroup is order 8 because the order was 4. So the size is 8, sorry. Write down the obvious thing. And I think this is again credit to Teja, who actually explicitly worked out the differentials and checked that the differential is square to 0. So you can write down M0 goes to this quotient of M0. Then you have the length 1, quote unquote length 1 elements dot 0, the quote unquote length 2 elements dot 0, length 3 elements dot 0, and then the unique longest element in the dihedral subgroup. So this is indeed a complex. Is it a resolution? Is the complex exact? And again, thanks to Teja for writing down these differentials. And so what is the answer? More generally, of course, you can have H min to consist of k different pairwise disjoint subsets. Some of them may be pairwise orthogonal, not all of them need to be. Can one write down the resolution using Verma modules? Now, when all these disjoint subsets have size 1, the answer is of course yes. That is the usual resolution of a parabolic Verma module by usual Verma modules. And because when all of them have size 1, then H min is, then M lambda H is a parabolic Verma. It's a first order module. And those are well known to be resolved. So certainly sanity checks hold. But what happens if even there are 2 holes and one of them is first order and one of them is second order and they are not disjoint? That is the example on this slide, and I don't know the answer. So, and okay, that is one part of it. Of course, the other part is, BGC resolutions should translate into something geometrically on the flag variety side. And like, so again, the parabolic Vermas and the usual Vermas and so on, like is good. But what about for this one? It's a second order Verma module. There's a second order hole in it. What does that go to in the flag variety side? And so what is the counterpart in geometry really, from which maybe one can deduce this resolution for SL4 and more generally for general semi-simple GUS. Okay, so again, I could stop here. We're already over time, or I can tell you about the last part and then we can stop after that. So at least I should give people a chance to run away if they want to. So, or for everybody to start. Amri, Raghavan. I mean, we can also stop recording and then I can continue for those.
Yeah, sorry, Apoorva, I have to go though.
Yeah, I too have to leave now.
And then start.
Okay, so yeah, so I guess that brings us to thanks, Apoorva, for taking the time and effort to explain this to us.
For coming. 3 talks, each of 90 minutes or 40, 75 minutes.